Today, we are going to talk about how to fix autocorrelation, and someone or some other people call it serial correlation. And there is a series of tests you're supposed to perform in order to correct this deficiency or these missed issues in your estimated model. First of all, I would look for a data. Let's try here. Okay, data. Okay, I have data on Russia. Let me just import this one. Click on OK. Okay. I'll close this one. Then I'll just pull this one or push it to the side. So let's go through a small note here. This is the classical assumption number 4. And we have to know that there is this term called uncorrelated error term in the model you have estimated. So serial correlation happens when some of the error terms takes the same form or the same shape of the previous error terms. So when these issues happen, we call this one serial correlation, which is the positive one. Then when the error term take the opposite sign of the previous error term, we call that one a negative serial correlation. How do we justify a serial correlation in our model? First, we need to check there is something called pure serial correlation, which happens when it is a natural thing, which happens when the model is correctly specified, and the impure is caused by when the model is not correctly specified. How do you detect this in your model? First, you need to run this test, or at a glance, you can see it from the Debye-Waxen figure or value you obtain in the estimated model. For instance, when you estimate a model, Debye-Waxen figure is automatically added to the estimated model. So we know that it's the accepted range for the Debye-Waxen is 1.5 to 2.5. Anything less or anything beyond this range is not acceptable. That means that the model is suffering from a serial correlation, which can be a negative or positive. So what do we do when we encounter these issues? This assumption that I'm going to explain here cut across everywhere, but the way of handling this, we will perform it using Gretl. First, how do we do this? It's the generalized least squared method. So, as we have gone through this quickly, okay, one more thing. Debye-Waxen is not capable of testing for high order serial correlation. So we have other tests like the Portmanteau. We have Briggs-Godfrey, which is the BG. We have which is the Portmanteau, which is the BP. So we will run our model and go through these steps in order to solve any issues of serial correlation, but the assumption is that the model should be correctly specified. So we need to make sure our model is suffering from the natural autocorrelated error terms. So we have to make sure we are here. We are in this range. First, let's go to Gretl. I'm not going to use all the variables because I don't think it is necessary for me, and I don't see any correlation between these kind of variables. But what I'm going to do is that, first of all, you can see from this side, when I go to model and go to ordinary least squares, I can put GDP per capita and then put all the variables. For instance, let's put all these variables here. and put these ones here. This is just an example. We have not started with our original task for today. So when we do this, we click on OK. What do you see? You can see a Debian waxing value here, which is less than the range we talk about, that is 1.5 to 2.5. So, and also you can see here that the coefficients are really large, and if you really want to have a uniform unit of measurement, let's convert these variables into logs. So what I'm going to do is that I will select everything here, then go to add, click on. So you can see here it's giving you a warning that generated missing values. So let's check the variables one by one as we have converted them into logs. So you can see youth unemployment, nothing is missing here. You can see from military spending, nothing is missing. You can see here to trade openness, nothing is missing. FDI, something is missing. So I wouldn't include FDI in my model that I'm going to estimate. Also, inflation, nothing is missing. GDP per capita, nothing is missing. Then real effective exchange rate, nothing is missing. So let's go back to our model. Now we are going to ordinarily square again. Click on it. Let's put this one, and then also select everything. I'll exclude FDI because I don't want any missing values from my model. And here I guess I need to remove this one because I'm going for the logs only. So how many items do we have? We have youth, we have military, we have trade openness, we have inflation, we have real effective exchange rate. So I think we are good to go. Now click on OK. So you can see these things, or these coefficients, are now looking good when we converted the variables into logs. But first, as I said here, our model should be suffering from pure serial correlation, which is caused by a correctly specified model. Let's go to test to run this test. And as you can see from here, to Debian waxing value is less than the range, which is acceptable. So let's go to test. Let's go to run Z, reset test, and click on all variants. You can see none of the model specification shows that the model is correctly specified. You can see from here, which is for squares and cubes. You can see for squares only. You can see for cubes only. At least if two of these things or this specification gives us a good p-value, then we could have rejected or stick to the alternate hypothesis. So you can see here that, you can see here that the p-values are less than 5%, and you have to understand that to accept that the model is correctly specified, these p-values must be greater than 5%. So here it indicates that the model is not correctly specified. What do we need to do? Here, okay, let me go to test again. We can also check for heteroscedasticity. We don't have any problem with heteroscedasticity here, which shows that there is no problem for heteroscedasticity. We can go to check about normality. You can see the error terms are normally distributed because the p-value is greater than 5%. You can close this one. Test again. We can test for autocorrelation. Like I said, since Debian waxing cannot test for high order, so let me increase this one to, let's say, 4. Now you can see there is autocorrelation here because look at the p-values, they are all less than 5% except this one, and you can see all the tests here. Look at this place, we have these here, the last one here, we have it here, we have this one also, Lagrange multiplier, which is also testing for autocorrelation. And you can see the test bridge Godfrey here. So whatever we've stated here is also in Gretl, and you can see from this side, you can see 2 of these tests are showing that there is a problem of autocorrelations. So since the model is not correctly specified, what do we have to do? Let's go back, close this one. Let's go to test. Here, not test, go to edit, since I don't want to go back to model and start everything again. So model, go to model. Now, sometimes these problems come from some of the coefficients. Not coefficient, yeah, coefficients are attached to the variables. So I will assume that there's a variable also causing this kind of incorrect specification. Incorrect specification happens when a variable is omitted from the equation or the model you are estimating. Also, it can happen that a variable is not supposed to be in the model, but you have included it in the model. First, what do I have to do? Maybe let me eliminate this one, military spending. So I will remove this one, click on OK. Now you can see the model is improving. You can see from here it's improving even by the Debin-Waxen value here. So I don't need this one anymore. I'll close this one. So you can see some of the variables also cause autocorrelation, and at the same time it causes incorrect specification. The next thing we are supposed to do here is that we go to test again. We test for reset or variant. Now you can see it is improving a bit, but there is still a problem. It shows that the model is still not correctly specified. At least I need 2 of these to pass the required conditions. So it is still not sufficient for us to conclude that the model is correctly specified. Now let's close this one. Then let's go to edit again, or if you want you can also perform other tests to confirm. You can see that there is still no heteroscedasticity, and you can also check for normality here, and you can see it's okay. You can close it. Now let's go to edit again, model. Then let me eliminate youth unemployment, sorry. Then click on OK. So you can see from this side that there is still a problem of autocorrelation here. Now what do? I'll first go to model, okay, and check if everything is okay. Yeah, everything is included here, and you can see from this side that since everything is okay, what we have to do, we have to go to test, Ramsey reset test, and we select all variants. Now you still can see that there is a problem with this issue of autocorrelation. So what do we do? First, I will also close this one, and okay, sorry, that was about incorrect specification. So let's go to modification again. I'll bring youth and then eliminate inflation. So let's see. Now you can see here that inflation was also causing a problem. So I can close this one, and what we need to do again is to perform the test again. So always what you need to do first is to check if the model is correctly specified. Like I said, we need to be in the pure serial correlation, which is caused by a correctly specified model, in order to resolve this issue. If it is impure, please do not continue, because it means that there is even a problem with your specification. Here, what we need to do now is to perform this test again, or variant. Now, bingo, you can see here, this is more than 5%. This is also more than 5%, but except this one, which is not more than 5%. So I would say that the model is maybe 90% or 95% correctly specified, because all these two of these tests is proving that the model is correctly specified because they are greater than 5%. Let's close this one. Then we have to perform the necessary test here as well. Let's check for this one again. Heteroscedasticity, you can also use the white test. This also shows that there is no heteroscedasticity. We can also check for using this one, Perspective. You can see that it also indicating that there is no problem with heteroscedasticity. Let's check for normality, and you can see it is normally distributed, the error terms. And now look at the Debye-Waxen value here. It's not even close to 1 or 1.5 that we need. So it is less than the acceptable range. And what we need to do, how do we correct this thing? That is where this one comes in. That is the GLS, which comes in here to help us fix this issue. But note that this also has a problem. When you're handling this one, remember that the coefficients will not remain the same, and some of your variables will tend to be, some of them might be significant here, but when you use the GLS, some of the variables will become insignificant. In other words, they will be not significant anymore. So what we need to do now is that we can also check for our last test here, autocorrelation, just to confirm. So you can see there is a problem here. There is still a problem, even though some people will agree that it's acceptable, but there is still a problem. Let's make sure we have fixed the Debye-Waxen issue here. So what do? We have seen this one, and we know that we are using the variables trade openness, real effective exchange rate, youth unemployment. So what I need to do is that I'll close this one. Now let's go to model. You go to model here in Gretl, you go here, you can see the GLS here. The assumption is that they are R1 here. Check here. So you click on this one. We are going to use all these tests here are applicable under the GLS test. So you don't need to do anything. Just choose one of these things or one of these items here, and it already selecting the first one. So you click on OK, and let's go down and see what happens. It's rerunning everything by using the standard errors and everything just to correct the Debye-Waxen figure. And now pay attention here. Let me just try again and rerun the ordinary least square here for you to see. So you can see here that something has happened. Here the coefficients are decreasing, and trade openness has tend not to be significant here. That is one aspect I talked about earlier on. And you can see that all the variables coefficients have been reduced. The R square has increased, you can see from here. And the assumption here is that the model is correctly specified. So you cannot do Ramsey reset. You can do normality. You can see normality, it has even increased, showing that it's really a normal distribution among the error terms. Look from this side. This is from the GLS. So I can also check normality here for you to see from the normal OLS for you to see normality. So you can see, look at this, look at the p-values. This is more efficient here, and it looks like a lot of things has been corrected using the GLS, just that the coefficient has been reduced. So let me close this one, and close this one. Also close this one as well. Also, I would go to test again and test for autoregressive conditional heteroscedasticity. So you can do that. I can increase this one, and I'll look here. It's giving me this, showing that there is no autoregressive conditional heteroscedasticity available in this or present in this model. So when you want to correct a Debye-Waxen value which is smaller than the acceptable range, that is 1.5 to 2.5, you can use the GLS model to resolve this issue. But always note that when you're handling this issue, it comes with some consequence, which sometimes some of the coefficients which are significant in the normal OLS becomes insignificant under the GLS model estimation. So equally, you can also try some of the other parts. We can try if sometimes it gives you error. Look, this one also works. The efficiency between these tests and the GLS are different. You can see here the Debye-Waxen value is reducing using the Paris option. So let's go to edit, modify. Usually, let's try this one. Now check this one here. It's also giving you the same thing like what we had in the first one, because this is just, I would say, an upgraded version of this one, because it's usually the same thing, nothing special, nothing different. So that is all about how to resolve your autocorrelation of first order where the Debye-Waxen value is smaller than the acceptable range. And also, the reason why I always want to do this with you right from the basics is that I wouldn't sit somewhere and just practice something over and over using some variables that will be easy for me to complete the task quickly as I can, so that you will not get any proper understanding. I always want us to go through the raw video so that we know what we are doing, and when any issues comes up, we will be able to resolve it. Thank you very much for your time, and pardon me for some of the mistakes or the grammatical errors in this video. I hope in the upcoming videos we will improve upon the grammatical errors in this video. Stay tuned and watch out for more from this channel. Thank you very much.